Hello dear students, today we will discuss very important properties of R which are actually called order properties of the set of real numbers. Okay. So what are order properties? Right, just let me Okay, so ordered properties are basically the less than, greater than, less than, these things that we had done in our school level. Say 3 is greater than 2, 5 is less than 7. Okay, these things are known to us. So when we say 3 is greater than 2, this actually means 3 minus 2 is positive. Okay, so order property is basically dividing the property of dividing the real numbers into 3 parts. One part is the set of positive real numbers, another part is the set of negative real numbers, and another part is the real number 0. Okay, 0 is neither positive nor negative. Okay, right? So this is basically the order property. Okay, it says that the set of real numbers can be we can find a set P inside the set of real numbers. Okay, so this P actually has the properties of positive real numbers. Okay, so and this set of negative real numbers, it's something like minus P. Okay, and this the set 0, this singleton set 0. Okay, this is just one element which is neither positive nor negative, and if we take the union of all this, we get the whole of real number system. Okay, so that is basically the motivation or idea behind the order property. Okay, means we need to define what are positive real numbers, what are negative real numbers. Okay, we need to define something called greater than, something called less than. Okay, so that we can work with these, or we can analyze these things. Okay, so the order properties, so as per Bartel and Shepard, the introductory part is the order properties of R refer to the notions of positivity and inequalities between the numbers. Okay. So the field axioms, they are not sufficient for our analysis of real numbers. Okay, we need something more. What is that? The order property. We need to have some idea about what is less than, what is greater than. Okay, which numbers are less, which numbers are more, or which number is positive, which number is negative. We need those ideas. Okay, that is why order property has to be taken care of. So as with the algebraic structure of the system of real numbers, we proceed by isolating 3 basic properties from which all other order properties can be derived. Okay, so in our school days we have seen if a is greater than 0, b is greater than 0, then a plus b is always greater than 0, right? Then if then from there a into b, this is also greater than 0, right? If a is greater than 0, b is less than 0, then a into b is actually less than 0. Okay, these are the properties of inequality which we have proved also in our these things school level. Okay, so out of all these properties, which are the fundamental, or which properties we can take as fundamental, very fundamental properties, and using those properties we can derive all other properties. Okay, so that is basically the motive behind listing the order properties. Okay, just like field axioms, I told you the algebraic properties of real numbers, we fix certain minimum number of properties which we take it for granted, and using those we prove all other properties. Okay, so here also for order properties we will try to list the minimum 1 or 2 properties which we will take as fundamental properties, we will accept without proof, and the other things we will derive it by proper proofs using these axioms or properties. Okay, so these are the order axioms or order properties, right? Okay, the simplest way to do this is to identify a special subset of R by using the notion of positivity. Okay, so we try to separate one set out of the set of real numbers, which is actually called the positive set of positive real numbers. So we will basically use this fact that if two numbers are positive, then the sum of those two numbers is also positive. We will take this as a property. Okay, so without further delay, let me just list out what are the order properties of R, or which properties we should take as fundamental properties, right? So the order properties of R, this the statement is this way: there is a non-empty subset P of R called, so we call that subset as called the set of positive real numbers. Okay, positive real numbers. Okay, so the intuition is the fact that sum of two positive real numbers is positive. Okay, if I add two positive real numbers A and B, their sum is going to be A plus B, which is also positive. Okay, like that. The intuition is this, and for proving taking our axiom, we denote this set of positive numbers as P. Okay, means it can actually be shown that if such a subset P of R exists which satisfies this properties listed, it has to be the set of all positive real numbers. Okay, there is no other option. So there is a non-empty subset P of R called the set of positive real numbers that satisfies. Okay, that satisfies. So P is such a set which satisfies the following properties. Okay, the following properties. Okay, so what are the properties I should list? Number one property is if A comma B belongs to P, right, then A plus B, A comma B belongs to P, then A plus B also belongs to P. Okay, right, so this is the order property, one of the order properties. So there are three fundamental properties which we will list. Okay, so this basically says that means it's motivated from the fact that the sum of two positive real numbers is going to be positive. Okay, so P is such a set of real numbers which satisfies this property: A plus B belongs to P whenever A and B belong to P. Okay, number two property is if A comma B belongs to P. Okay, the other thing that I had listed, the product, then if we multiply two positive quantities, the product is positive. Okay, so if A comma B belongs to P, then A into B, this is also in P. Okay, this is another property. And the third one is if A belongs to R, then exactly one of the following holds. Okay, exactly one of the following holds. Okay, what are those? Exactly one of the following holds. These are A equal to 0, or A belongs to P, or A minus A belongs to P. Okay, right. So exactly one of these holds. So this law is called the law of trichotomy. So this is also written in the introductory pages of any textbook of class 10. You see of real numbers. Okay, it's written there. Of course, in a different form. It's not written exactly in this way. It's written something like if given any real number A, then either A is greater than 0, or A is equal to 0, or A is less than 0. Okay, so these are the exactly one of this is true. Okay, means any given real number is either positive or negative or 0. Okay, this is basically the law of trichotomy. Okay, so these three are our order properties of R. Okay, these are the three assumptions that if we are given any real number, only one possibility is there out of three possibilities. It is either positive or it is negative or it is 0. Okay, there is no other possibility. Okay, so that is what. So the first condition, two conditions ensure the compatibility of order with the operations of addition and multiplication. So the set of positive integers is closed under addition operation. Okay, so P is closed under addition, P is closed under multiplication. Okay, and the third one is called the law of trichotomy. Okay, right. So okay, so either A is 0 or A is positive, or minus A is positive. Minus A is positive means A is negative. Okay, that is what we say. Okay. So using these properties, let us note something. Note that. So if in your exam the question comes, what are the order properties of R, then you will just write this particular statement. Okay. Order properties of R, just give the heading. There exists, or there is a non-empty subset P of R called the set of positive real numbers that satisfies the following properties. Okay, so these are actually called the order properties of R. So note that if A belongs to P, we write. So we introduce a simpler notation now, which is in agreement with whatever we have done in school. Okay, so instead of writing always A belongs to P, let us introduce another symbol which is called A greater than 0. If A belongs to P, means if A is a positive real number, we write A greater than 0. Okay, so the meaning of A greater than 0 is that A belongs to this particular set. Okay, P. So if A belongs to P, we write A greater than 0, and we say that A is a positive real number. Okay, so this A and this A are different. This A is the element that we have selected, and this A is the article A, grammatical article. So we say that A is a positive real number. Okay, real number, right? Yeah. So if minus A belongs to P, then we write A is less than 0, and we say that A is a, and we say that A is a negative real number. Okay, negative. So let me just put this one in quotation. A is a negative real number. Okay. Also, if A belongs to P union 0, means I do not know whether A is positive, means I am sure that either A is positive or A is 0. Okay, so that in that case A belongs to P union singleton 0, then we write A greater than or equal to 0. Okay, greater than or equal to 0, and say that A is non-negative. Okay, non-negative. It's not negative. It's either 0 or positive. Okay, non-negative real number. Right. If A belongs to P union singleton 0, then we write A greater than or equal to 0 and say that A is a non-negative real number. Okay. Similarly, if minus A belongs to P union singleton 0, then we write A is less than or equal to 0, and say that A is non-positive. Okay, non-positive real number. Okay, so one is non-negative, another is non-positive real number. Okay. Right. Okay. Right. So so now we defined the notion of inequality between definition of inequality between two numbers. Okay, definition of the concept of inequality. Okay, so let A comma B belongs to R. Number 1, if A minus B, so under what condition we say A is greater than B? Okay, so we say that A is greater than B if A minus B is positive. Okay, so in terms of this set order properties, we will write it this way: if A minus B belongs to P, okay, then A is greater than, we write so symbolically we write A is greater than B, or we write it this way: B is less than A. Okay, right. So number 2, if A minus B belongs to P union singleton 0, okay, then we write A is greater than or equal to B, or B is later than, means this is another way of writing, not this way, or B is less than or equal to A. Okay, like that. So this is the definition of inequality. So whenever we want to show that A is greater than B, we will actually show A minus B is greater than 0. Okay, means it belongs to P. Okay, so subsequently in our further notations, we will always use A minus B greater than 0 instead of writing A minus B belongs to P always. Okay, so once we understand the concept, it's okay, right? Yeah. Thus, the law of trichotomy, or the law of trichotomy can be equivalently written this way. Okay, equivalently written as this: given any real numbers A comma B, only one of the only one of the following is true. Okay, what is that? So we have already seen what was the law of trichotomy. Given any A in R, exactly one of the following is true: A is 0, or A is in P, or minus A is in P. So here, instead we are given two real numbers, we compare it this way: exactly one of the following is true. That means either A minus B is greater than 0, or A minus B is equal to 0, or A minus B is less than 0. Okay, so either A is greater than B, or A is equal to B, or A is less than B. Okay, right. Okay, so exactly one of the following is true: A minus B is greater than 0, or A minus or B is equal to 0, or A minus B is less than 0. That is, A is greater than B, or A is equal to B, or, so out of these three cases, exactly one of them is true. Okay, so this is another way of writing the law of trichotomy. Okay, so this is basically the way which was given in our class 10 school textbooks. Okay, even though these are not very much discussed in school level, okay, but I feel this should be discussed. Okay, so for so thus if we have A less than or equal to B, thus A less than or equal to B if both A less than or equal to B and B A greater than or equal to B are true or satisfied, then A should be equal to B. Right, because only one of them is true, so it cannot be A strictly less than B, it cannot be true. Right, because in that case both are getting true. No? A less than B, less than or equal to B, so here both are satisfied. So if A is strictly less than B, then for this one to be true, A greater than or equal to B to be true, it should satisfy A equal to B. Okay, but in that case it is again violating the law of trichotomy. Okay, so that is why if A less than or equal to B as well as A greater than or equal to B, okay, then we can always write A is equal to B. Okay, so this is very much used in analysis. Okay, we show that something is less than or equal to, or something is y is less than or equal to, some expression is less than or equal to this. Again, this expression is less than or equal to this. So these two have to be equal actually, right? Say something like alpha less than or equal to beta. Once we show alpha is less than or equal to beta, after some other modification we show that beta is less than or equal to alpha. So from these two we can conclude that alpha is actually equal to beta. Okay, so this is a very standard way of showing equality of two numbers in analysis. Okay, so it follows from the law of trichotomy, because exactly one of them has to be true. Okay, right. Okay, so another note is when we write A less than B less than C, the notation. So when we write this, it actually means what? Notation, this means A is less than B and B is less than C. Means both of these are satisfied, right? A is less than B and B is less than C. So that thing we write it as A less than B less than C. Okay. So now there are some theorems which we can easily verify. So these are actually the properties of inequalities which will follow from the order properties. Okay, let A, B, C belongs to R. Number one, if A greater than B and B greater than C, then A is greater than C. Okay, right. Number two is if A is so this is actually called the transitive property. Okay, transitive property, right? If A is greater than B and B greater than C, then we can conclude that A is actually greater than C. Number two is if A is greater than B, then A plus C, whatever number C you take, is always greater than B plus C for all C inside R. Okay, if we add the same number to both sides of this inequality, the inequality remains the same. Okay, so inequality doesn't change in that case. Number three is if I multiply both sides by number C, then in that case there are two cases. If A greater than B and C greater than 0, then AC will be greater than BC. Okay, and if A greater than B but C is less than 0, okay, in that case then the inequality will get reversed. AC is strictly less than BC. Okay, so these are the three very important properties, very well known properties which follow from the order properties of R. Okay, right. Okay, so how do you prove it? Okay, proof. So number one is given A is greater than B and B is greater than C. That means what? So this actually means by our definition of this, see the definition of inequality, A is greater than B, this actually means A minus B belongs to P. Okay, so A minus B is greater than 0, or that is A minus B belongs to P. Okay, and B minus C also belongs to P. Okay, so by order property of R, we have so these two are elements of P, and by order property, what was the order property? That sum of two elements in P is also an element in P. Okay, so this follows from the order property of R. By order property of R, this A minus B plus B minus C, this is also an element inside P. So this implies, if I just use associative law, this is A minus B plus B minus C, this is an element in P. So this implies A minus C is in P. So A minus C is in P means actually A is greater than C. Okay, right? So by order property of R. Okay, so P here is the set of positive real numbers. Okay, so P is set of positive real numbers. Positive real numbers. Okay, so the set that we have taken in while defining the order property or listing the order properties. Okay, so A greater than B, so implies A minus B greater than 0. Okay, so that is A minus B belongs to P. Okay, so why we are doing it this way? Because here also you see we do not know anything about these properties. Okay, we are trying to prove it from the properties that we have listed, that if P is closed under addition, can we derive those properties? Okay, so we have seen that yes, using the fact that P is closed under addition, we can actually derive this transitive property. Okay, that is why we have to use it. Okay, don't means take it as something trivial. Why we are using this? We are using this because at this moment we do not know any of the properties of inequalities. We just know the order properties. Okay, right? So using that, so we are in a very preliminary stage. Okay, assume that you do not know any mathematics, any real analysis till now. Okay, any properties of real, less than, greater than. Okay, nothing is known to you. Just think that I know only these three properties. Using that, can I derive all other properties? Okay, that is the essence. This is the motive of this real analysis course. Okay, right? So the second one is also similar. Given A is greater than B. Okay, so A minus B is an element in P. Okay, A minus B belongs to P, right? And now what I have to show? I have to show that A plus C is greater than B plus C. Okay, so what did I tell you? If I want to show that A is greater than B, always I will use this definition. Okay, A is greater than B means I have to show that A minus B belongs to P. A minus B is positive. Okay, so I'll try to show that A plus C minus B plus C is positive. Okay, so we have A plus C minus B plus C. Okay, if I can show that this also belongs to P, okay, then we are done. So A plus C minus B plus C is actually, if I just use this law of this algebra, field axioms algebra, yesterday we had done, minus of A plus B is same as minus A minus B. Okay, we have derived this property already, so I can use that property and then I can just cancel this out. A plus C, so this becomes A minus B, which belongs to P. Thus A plus C is greater than B plus C. Okay, so this is basically the proof. Okay, A is greater than B, so A minus B belongs to P. So A plus C minus B plus C, so this is also a member in P. Okay, of course, right? So we have shown transitive property. Number 3 is I have to show that given A greater than B and C is greater than 0. Okay, so what we have, A minus B is an element in P. Okay, also and C is an element in P. Okay, C greater than 0, that means what? C is an element in P. Okay, and by order property of R, so we are using the second order property now, that P is closed under multiplication. Okay, so by order property of R, that is here P is closed under multiplication. Okay, multiplication. So what do I do? Please, P is closed under multiplication. So A minus B dot C, this is an element in P. So from here I can write AC minus BC. I use the distributive property here. This belongs to P. So from here, this means that by our definition of inequality, AC is greater than BC. Okay, So that is the thing. Clear? Okay, of course you can do it instead of writing belongs to P, but it will be better if you write it this way, so that you can get the idea of what is the order property. Okay, of course you can do it this way also. A minus B is greater than 0, B minus C is greater than 0. Okay, then by order property, the sum of these two, A minus B plus B minus C, has to be greater than 0. Okay, this follows from the order property. This is exactly what we have written in a different way. Belongs means instead of writing greater than 0, we have written belongs to P. Okay, so make it a habit to do it this way. The initial properties. Okay, later on we'll just carry on with our greater than symbol. Okay, right. Okay, so the only one part I have proved. The other part is next part is given A is greater than B and C is less than 0. Okay, so A minus B is an element in P, and minus C is less than 0 means minus C belongs to P. Okay, so by order property again, the product of these two is in P. By order property of R, A minus B multiplied with minus C, this is in P. Okay, so if you multiply, we have already seen A into minus C and minus B into minus C, this is in P. Okay, so A into minus C is minus AC, this we have already done, and B into minus C, this also I can write it as minus 1 into BC. Okay, so this will be just plus BC belongs to P. So what I have shown that BC minus AC, this is an element in P. Okay, so from there BC is greater than AC. Okay, or the other way I can write it as AC is less than BC. The inequality gets reversed. Okay, so if we multiply the both sides of an inequality by a negative number, the inequality gets reversed. Okay, so you have to understand this part, right? Okay, so we have to be very careful while multiplying both sides of an inequality by this a real number. Okay, so if we multiply by negative, inequality has to get reversed. Okay, so it is natural that the natural numbers are positive real numbers. This property is derived from the basic properties of order. The key observation is that the square of any non-zero real number is positive. Okay, so another theorem we will do. If A belongs to R, if A is a real number, then A square is always, A square is actually A into A. This is greater than 0, greater than or equal to 0. Okay, A belongs to R and A not equal to 0. A not equal to 0, then S square is always positive. Okay, number 2 property, 1 is always greater than 0. Okay, so see, we do not know about this also, right? We have to derive it from the order properties. Okay, so as of now we do not know whether 1 is greater than 0 or not. Okay, number 3 is if n belongs to natural number, then n is greater than 0. Okay, so how do I show these things? Okay, so solution is S square. So given A in R, we have S square is also a real number. Okay, it follows by property of this closure property of multiplication. Okay, so we will use that here. So if A is non-zero, then either A belongs to P or A minus A belongs to P. Okay, yeah, so we can do it this way. Given A is not equal to 0. Okay, so by law of trichotomy, so trichotomy says that exactly one of the three options will be true. So here we see that this option itself is incorrect. Means A is not equal to 0, means A equal to 0 is false. The other two, one of the other two has to be correct. So by law of trichotomy, we have either A is greater than 0 or A is less than 0. Okay, that is A is greater than 0 means A belongs to P. Okay, let me write it this way: A belongs to P or minus A belongs to P. Okay, let me write it this way. So let us consider these two cases separately. Okay, either this or this, but not both. Okay, not both. So if A belongs to P, then by order property again, what about A dot A? A dot A belongs to P. That is, what is A dot A? A dot A is A square, because by order property it says that P is closed under multiplication. So A square belongs to P. Okay, right? So that is A square is greater than 0. Right? Okay. The next thing is, if minus A belongs to P. Okay, then what we can do? If minus A belongs to P, then by order property again, we get minus A into minus A. This is also in P. Okay, so that is, but we have already done in our last class this field axioms. From field axioms it follows that minus A into minus B, and this is same as AB. Okay, this already we had done this. So from there what we can do is minus A into minus A will be actually A square. This is nothing but so let me write it in two step. That is, A dot A belongs to P. Okay, that is A square belongs to P. Okay, so in all cases, thus A belongs to R with A not equal to 0 implies A square is greater than 0. Okay, so this is what we have proved, right? Okay, right. So yeah, so we have used this property which we had already proved. Okay, so now the next one, 1 greater than 0. Okay, how will I prove 1 is greater than 0? So we have 1 belongs to R, and 1 is 1 square. Okay, 1 belongs to R and 1 is non-zero. Okay, so we will just use the earlier property that we have done. So by the earlier property, 1 square is greater than 0. So that is, 1 square is what? 1 square is again 1. 1 is greater than 0. Okay, so using this earlier property itself we can do it. Okay, if A belongs to R and A is non-zero, then A square has to be positive. Okay, clear? So here we are using the fact that 1 square is positive, but 1 square is again 1, so 1 has to be positive. Okay, so you see, means we are using the fact that square of any real number is positive. Using that, we are showing that 1 has to be greater than 0. Okay, that is the thing. So we are deriving everything from the axioms. Number C or number 3, we have to prove that if n belongs to a natural number, then n has to be greater than 0. Okay. So we will use mathematical induction here. So we have 1 greater than 0. So this is, we have 1 greater than 0. So for n equal to 1, the result is true. Okay. The result is true means yeah. So let me write this to prove n belongs to natural number implies that n is greater than 0. Okay, so we have 1 greater than 0. So for n equal to 1, the result is true. Okay, the result is true. Okay, so let us take the induction hypothesis. Let the hypothesis be true. Let the result be true for n equal to, say, k. Okay, that is n equal to k, which belongs to natural number. That is, k is greater than 0. Right now, 1 greater than 0, comma k greater than 0. Okay, 1 greater than 0 is already known to us. So, and we have assumed the induction hypothesis as k is greater than 0. Now 1 greater than 0 and k greater than 0. So, by order property, it will follow that. It follows that 1 plus k, this is also greater than 0. Okay, so the result is true for n equal to k plus 1, right? If we assume that the result is true for n equal to k, then it is also true for n equal to k plus 1. So by principle of mathematical induction. So by principle of mathematical induction, so which you have already done in higher secondary. So principle of mathematical induction, the result is true for all n belongs to natural numbers. Okay, that is, n belongs to natural number implies n is greater than 0. Okay, so all natural numbers are positive, right? Okay, so there are some other properties which we will do in the next lecture. Thank you. So you please go through these properties that I have listed, and next day we will continue.